Start sharing. Okay. Can you all hear me?
Yes, sir.
Yes, sir.
Okay. So any questions from the previous class? I'm sorry, last class was, as I said, a bit of a issue because I think half the class was not heard, and sometimes as a teacher you never are able to reproduce what you said earlier. Uh, just 15 minutes earlier, repeating it again is a bit of a problem. But anyway, to quickly summarize, there are two aspects to plasmid instability of plasmids, which is the emergence of plasmid free cells. One, as I said, is the emergence of plasmid free cells, which happens because there's a probability that some cells, daughter cells, do not get the plasmid and they become plasmid free. And then is the overtaking by the plasmid free cells of the whole population of plasmid containing cells. Because remember that the emergence is a very small fraction. And as I said, I could also sort of divide this process of emergence and overtaking into two very interesting components. For example, I can write that there are, to convert stability to make it stable, there are active mechanisms of ensuring stability and passive mechanisms of ensuring stability. What would be a passive mechanism? A passive mechanism would be which, for example, reduces the probability of emergence of plasmid free cells. For example, the whole argument that I was giving in the last class of converting multimers to monomers is a passive mechanism, because what it does is that it reduces the probability of plasmid free cell emergence. If I convert a monomer to, so because the probability of plasmid free cell emergence is given by p raised to 2 raised to 1 minus n, where n is the discrete copies. If n is a discrete copy of plasmids, discrete number of copies, so obviously a multimer being converted to monomer, this process here is actually going to increase n, the number of discrete copies. Remember that the copy number is copy number of large, high copy number plasmids, sorry. The copy number of high copy number plasmids is controlled by the interaction that the plasmid origin has with the cell. And so what the cell allows is a certain number of origins. And these number of origins would mean more plasmids. More origins, more number of plasmids. But these plasmids could be entangled in a multimer, in which case they will be inherited by one or the other of the daughter cells. So n being the discrete copy number, conversion of multimers to monomers would reduce P and hence reduce the probability. Similarly, I talked about the PAR locus. The PAR locus, the partition locus, the PAR locus, which was a mechanism used by low copy number plasmids to ensure that, when the cell divides, the septum formation takes place here, and the plasmids sort of attach to the septum in this way, thereby ensuring that the daughter cells are actually on either side, the plasmids are on either side of the daughter cell that is going to form. Thereby, theoretically, at least it making P equal to 0. And it is close to 0 because, as you know, that this happens with low copy number plasmids. And low copy number plasmids interestingly turn out to have very high stability, primarily because the daughter cells inherit one plasmid each out of a pair. So if there are 2 pairs or 3 pairs, 2 pairs means two plasmids will go to each of the daughter cells. So the PAR locus also, as you can notice, is a passive mechanism. It prevents or reduces the possibility of emergence of plasmid free cells. Is this clear? This is what we were talking about in the last class. On the other hand, an active mechanism would be where you are actually actively working against plasmid free cells. So all cells which are plasmid free cells, if they are somehow killed, if they are killed, or they are not allowed to survive, or the growth rate is reduced, then that is an active mechanism of ensuring plasmid stability. So you want to ensure stability, you can have an active mechanism. And the most obvious active mechanism, sorry, this is the problem. This is a software glitch. Can you hear me now?
Yes,
Yes,
sir, we
sir.
can hear you.
But you can't see the screen, right?
Not yet, sir.
No, now we
Okay.
can.
Now we can.
Now you can. Now you can. See, this is the problem. This is a glitch in the software. It sort of, and we are back exactly at the same point where we were earlier. You can see
Yes, sir.
everything, right? Yes, sir. Okay. So yeah, that's why I need to keep this pop on active here on the right side bottom, so that I know that things have suddenly gone off. So yeah. So otherwise we would have had the same tragedy as previous class. So the plasmid free cells are killed, and the most obvious example that I talked about was antibiotics. Where I said, for example, when you add ampicillin into the medium, what happens is that very clearly ampicillin resistant cells only can grow. You add ampicillin into the medium, ampicillin is added into the medium, and this ampicillin in the medium will ensure that only the plasmid carrying cells, which also can contain the AMP resistant gene, will survive, and the plasmid free cells, which do not carry the AMP resistant gene, will not be able to grow and die. So those are active mechanisms. So most of the time, active mechanisms work on the overtaking part, and most of the time, passive mechanisms work on reducing the emergence part. But that's not always true, but most of the time. So really, preventing overtaking by active mechanisms would be essentially called post-segregational, because you're segregating the plasma, post-segregational killing. I should actually call it post-segregational killing of plasmid free cells. I mean, of course, of plasmid free cells. Post-segregational killing of plasmid free cells is achieved by antibiotic. So plasmid free cells are going to emerge randomly because of improper partitioning, etc., etc. But once they emerge, they are not able to grow, or they're killed because of the presence of ampicillin in the medium. So this is a very active mechanism, post-segregational killing of plasmid free cells, right? And we can achieve this by the simple expedient of adding ampicillin, of course, with the caveat that I said about in the last class, which was that ampicillin is actually degraded. Ampicillin is actually degraded by the ampicillin gene. It actually degrades ampicillin, and therefore, because it degrades ampicillin, you could end up in a situation where the plasmid containing cells, the X plus cells, let me call it, X plus cells, somehow provide protection, provide protection to the X minus cells, protect X minus cells by actually leaching enough beta lactamase, which degrades. So you actually degrade the ampicillin, and this degradation of ampicillin provides the protection that you are seeking for the X minus cells. It protects the X minus cells because ampicillin is degraded by the gene, and therefore X minus cells can actually emerge under the protection of X plus cells. This usually happens, as I said, with high cell density culture. And this is what you are trying to grow in the fermenter. I hope you know why we want to grow high cell density cultures. Can you tell me one reason why? Why are you interested in high cell density cultures in a fermenter? Can any of you give me a reason why I suddenly mentioned the word high cell density cultures?
For producing high amount of products.
Yes, because the whole idea, yeah, absolutely, absolutely, perfectly correct. So the product form is a function of the number of cells, because each cell is producing a certain amount of product. So because each cell is producing a certain amount of product, the higher the cell density, the higher is the amount of product form. So obviously, because you want to make a lot of product per unit volume, you are also forced to go for high cell density cultures, and therefore, by definition, your high cell density culture is the situation which actually allows the emergence of X minus cells. Now, obviously, therefore, ampicillin is not a very good choice because it sort of leaches out into the medium. Though there are other antibiotics. I'll clear the canvas. Yeah. So there are other antibiotics, and a very common antibiotic is kanamycin. Sorry, kanamycin, which is also, we have a can resistant gene, just like AMP resistant gene, which provides, but the kanamycin resistant gene is a kanamycin aminoglycoside. It's an aminoglycoside, so it is actually remains the gene product, the protein actually. When I say kanamycin resistant gene, obviously the gene is inside. I mean the protein that is produced to convert the kanamycin into an inactive form, this protein remains inside the cell. Remains inside. So the media which you, in this case, you are going to add what? You are going to add kanamycin, because obviously the resistance has to be kanamycin. So in the media you add kanamycin. This kanamycin does not degrade. So because it does not degrade, unlike ampicillin, the X plus cells, while they are producing the kanamycin resistant protein, they protect only themselves. They do not protect the X minus cells. X minus cells are not protected, and therefore, unlike ampicillin, where you have to keep adding extra ampicillin in high cell density cultures from time to time to take care of the amount that has got degraded, in kanamycin you don't have to keep adding extra kanamycin because it is not degraded. Of course, there is a certain amount of degradation of any antibiotic in a fermentation culture because of high temperature, agitation, aeration, etc., etc. That's negligible. That's something which does not require so much of corrective action. Now, the interesting point is that, well, before I go into that, the more interesting point is when we grow, these are for E. coli, and we have been only talking of E. coli, but think about yeast cultures like Pichia, Pasteuris, or Saccharomyces cerevisiae, or etc., etc. Now, these cultures, obviously, I hope you are familiar or you've heard this, these cultures often carry what is called the multi-drug resistant gene. They have resistance to a variety, because they have the multi-drug resistance gene is not resistance to a particular single ampicillin or kanamycin or anything. They have resistance across a series of drugs. Essentially, though I don't want to get into molecular biology here, we are going too far. The multi-drug resistance gene, the MDR gene, as it were, is actually a transporter. It picks up antibiotics and pushes them out of the cell. So these are actually very efficient transporters of drugs, and so actually by pushing out the antibiotic, it protects the cell against the antibiotic. And so the real point is that there is no such thing as an antibiotic resistant gene, because each cell naturally carries resistance to a range of antibiotics. So you cannot use ampicillin or any antibiotic as a selection marker. You understand what I mean by selection? Antibiotic as a selection marker. So selection marker means something which will select for your desired, because remember that what were we having? We were having the plasmid, which is carrying the gene of your interest, which is what you want to insert into the cell, because that is what will finally produce the protein. And this also carries a selection marker, the ampicillin resistance. And this ampicillin resistance gene is what distinguishes the fact that the X plus cells from the X minus cells, because X plus cells can grow on ampicillin, X minus cells cannot grow on ampicillin. And therefore, you are only interested in X plus cells because X plus cells also carry this stuff. Right? This is something which you would have done in the last practical, yesterday's practical as well. Now, since you cannot use antibiotic as a selection marker, what do? So now you reverse the argument. Now here the selection was, in a sense, you added antibiotic. So your antibiotic was present in the medium and you had resistance. You can do exactly the reverse. What is the reverse? Can you think of it? You added antibiotic added. Now you can do the opposite thing. You can actually subtract. For example, instead of ampicillin resistance as the selection marker, I cannot have it. So suppose I say that I will now introduce one of the genes for, say, leucine synthesis. Now leucine synthesis is a multi-step pathway, and let us say one critical step of leucine synthesis is done by a gene. Let us say there are various genes, so we call it LEU1, LEU2, LEU3, LEU4, and so on. So let us say LEU2 is being introduced, and in the chromosome of the cell, we ensure that LEU2 is absent. Now what will this do? If LEU2 is absent in the chromosome and LEU2 is only present on the plasmid, then in the absence of the plasmid being inside the cell would die. No, it would not die. Cell would die only when what happens? Only when leucine is not available. Are you with me till now?
Yes, sir.
So what am I saying? What I'm simply saying that suppose leucine was available in the medium, then the cell would not require to synthesize leucine. Think of human beings. Human beings do need a lot of amino acids, right? Can you mention some of the amino acids that we need from outside? Because we cannot synthesize those amino acids. And so we don't eat appropriate balanced diet, we will be very, very sick. Certain vitamins, certain amino acids. So we are auxotrophs. The word uses auxotrophs. So auxotrophs means that if in the absence of that particular nutrient, the cell would die. So the cell here, because LEU2 is absent in the chromosome of the cell has suddenly become an auxotroph of leucine. So when leucine is not available, the cell would die because LEU2 gene has been knocked out or somehow removed from the chromosome. And what you have done, that you have taken this LEU2 gene and put it onto a plasmid. So now what this plasmid is therefore doing, the plasmid is essentially doing exactly the opposite of what the antibiotic was doing. It is now providing not resistance to antibiotic, but the ability to remove this auxotrophy, and therefore we call this as auxotrophic complementation. Have you heard this term?
Yes, sir.
Yes, sir.
So we are doing auxotrophic complementation, and LEU2 is essentially in the so many plasmids do a lot of auxotrophic complementation even in nature. They contain genes which are very important for various properties that the cell may or may not need for its survival. And as a matter of fact, there's a lot of plasmid biology studies, which I will not go into, which allows these things to happen. So therefore, we have a situation where the absence, the plasmid, so the X plus cells will be able to grow, and that is the whole idea of selection, and X minus cells cannot grow only when leucine 2 is absent, or where leucine is not available. Now, obviously, when leucine is not available, X minus cannot grow, X plus can grow, and therefore your plasmid has selection marker. Now, this leads to very interesting and peculiar problems in actual fermentation technology. And this is the following, that it really means that your media has to be well defined. Has to be well defined. Now, if you go to the industry fellow and say ki, your media now has to be well defined because it should not contain, it should be leucine minus, he is going to get very, very angry, because he is used, especially in India, to pick up yeast extract or peptone, or worse, distillery waste, or animal waste. Animal waste, you know where it is available if you ever gone to East Delhi and beyond. So you know that's a very interesting place to go to, but that's the stuff that you can actually use in a very cheap way to provide the nitrogen sources and complex vitamins and everything. Nitrogen and all complex sources can very easily be available from things like animal waste or distillery waste or yeast extract or peptone. But unfortunately, this complex nitrogen source, which is a very cheap and a very easy raw material for bacterial growth, suddenly becomes non-usable because it also contains leucine. So you end up in a situation where you now can no longer use complex nitrogen sources because leucine is also being provided. So X minus cells will be actually protected because they can also grow, because you want to ensure that leucine is not available. So now this creates a serious problem, and there are very clever solutions where you actually add complex nitrogen sources in such a slow rate, complex N sources in such a slow rate that at any given point the leucine concentrations are very low. You add it very slowly, and leucine, the amount of leucine actually present, it is not that leucine is not available, but leucine concentrations are low, and therefore X minus cells are not really able to grow. Or even if they are able to grow, they are constrained by the amount of leucine available in the medium. So it is not a requirement that leucine should be zero. It should be it should be tending to zero, not really equal to zero, as long as X minus has a growth rate mu minus which is lower than or lesser than mu plus. Because mu plus is able to synthesize leucine, it does not depend on leucine for growth rate, therefore it is able to grow faster. As long as it is able to grow faster, it will not allow mu minus to overtake mu plus. Now, try to understand that the same argument can be used for antibiotics as well. You don't want to add a large amount of antibiotics and waste the culture and create trouble for yourself later on, because that antibiotic is going to go into the environment, whether it's ampicillin or kanamycin. You actually don't want to make mu minus equal to zero. You add enough antibiotic into the system such that X minus cells have a mu minus which is less than mu plus. Job done. You really are not bothered about the fact that there is 1% instability or 0.1% instability. You are bothered when the instability becomes 10% or 20% or 30%. And since, remember, P, the emergence of plasmid free cells, was very small, therefore, as long as mu minus is less than mu plus, you will not have overtaking taking place of the mu plus cells by mu minus cells or X plus cells by X minus cells. Are you getting this argument? So really, whether it is auxotrophy, which is a negative selection, complementation of auxotrophy, or it is antibiotic where you are killing the cells, the only thing you need to ensure is that mu minus is less than mu plus. You don't need to make mu minus equal to zero in order to ensure stability. And therefore, your strategy should be more subtle, should be more gentle, and you can allow a certain amount of complex nitrogen sources. Why do I want to allow complex nitrogen sources? Because otherwise, complex nitrogen sources carry all kinds of micronutrients, vitamins, minerals, which might be necessary for growth. A well-defined media is extremely expensive to formulate. It might appear that it is cheaper, it is not, because it requires microscopic amounts of vitamins or minerals or whatever, and that makes trace elements, that makes the thing very costly. If I'm allowed to add a very small amount of complex nitrogen source that carries with itself naturally, it is like those wonderful ads which you guys must be seeing, na? Ki, this bread contains so many minerals, so many this, so many that. Basically, it carries so many elements, iron, this, that. Actually, what the person is doing is simply taking wheat and crushing it and giving whole wheat bread. Instead of calling it whole wheat bread, he says it contains all the stuff that the surface of the what's called in Hindi choker, the wheat surface contains a lot of minerals which get removed when you don't make whole wheat bread, when you make it out of maida. Now, if you add the stuff which used to be earlier thrown away by people, by traditional people, now if you take the surface of the wheat and crush everything and you make a whole wheat bread, you will carry all the minerals with it. And then you can write in your advertisement that my bread contains all the minerals. So you can do this clever trick, which is used by advertisers a lot, that they take natural products and they study scientific literature to find out when you take natural products and you do not do too much of refining, what are all the vitamins and minerals it contains, and say, well, all these are present in your product. Which is, of course, simply saying that I did not remove it in the first place. It was always there, but I did not remove it this time. So that is the same argument with complex nitrogen sources. You just add complex nitrogen source, it will by definition carry with itself very, very small components of growth media which are absolutely essential for growth, which is not available in well-defined media. And so your cost goes down. But it will also carry leucine. So your resistance to that extent is reduced. But as long as you ensure that mu minus is less than mu plus, your job is done. Is this argument clear to you? So you have to have a very subtle and clever way. Yeah, go ahead. Sorry?
No, sir, I was not saying anything.
Okay. Okay. Now, any questions? Any questions that hit your mind, all of you? Yeah, so you realize that stability is not about a 0-1 sequence. Stability is a more complex and clever technology whereby you have to see that the growth rate is lower than mu plus and p values are small, and that p values and these two things taken together are what make life easy. So it is a very complex debate. I mean, and I'll come to that in a minute. We will make this. So is this argument clear to all of you? So now, yes, interestingly, the story doesn't end there. Plasmids also contain within themselves, and this is to answer the question. Plasmids, they also contain genes which are active selectors. I mean, we could have active selections and we could have passive selection. Remember that they contain genes which may be essential for growth or essential for providing various properties that help the growth of the cell, but they also contain genes. For example, one of the very interesting plasmids that exist in nature are what I call, well, let me not get into the technical. Let me think of some other term which I don't want to get into molecular biology too much. They contain a toxin antitoxin pair. Let me call it. So they contain two proteins which form a toxin antitoxin pair. And this is a very large range of toxin and toxins. I'm just giving you the most general example: Hox, SOC proteins and SEC-AB proteins and all kinds of literature is available. It's a very huge body of literature. I'm sort of trying to summarize this in the simplest way possible. Now, the toxin-antitoxin pair, so this is a gene here, which is now divided into two parts. There are two genes here. One is the toxin. Okay, and the other is the antitoxin. Now, when the plasmid is inside, the plasmid is already inside. So let us forget, one is the antidote, antitoxin. The antitoxin is the antidote to the toxin. Now, this plasmid is inside the cell, remember, right? So the toxin is being produced and it is being neutralized by the antitoxin. So now the toxin has a reasonably long half-life, long half-life, which means that it stays inside the cell for a long amount of time. But of course it does not, because it gets neutralized immediately. But if there was no antitoxin, it would stay inside for a long time, inside the cell. It will be produced and be inside the cell. Now, this production of the toxin, which is, as I said, is inside the cell, is being neutralized by this antitoxin. Now, suppose the plasmid is lost. The antitoxin has a very low half-life. The antitoxin, this has a low half-life. So the antitoxin tends to degrade very fast and the toxin remains, because the plasmid is lost, both toxin and antitoxin production are gone. And therefore, the cell is now faced with active toxin, which is not getting neutralized, and that kills the cell. So the loss of the plasmid immediately leads to cell death, independent of whether there was any selective mechanism in the medium. So there is no question of selective media. Okay, so the cell will die if the plasmid is lost. Because once the plasmid gets inside, it ensures its own survival. As long as the plasmid is not inside, no problems. You can have cells normally growing merrily. But once you have introduced this plasmid inside the cell, it becomes like this dangerous parasite. It is like our great COVID. It is now there, it is there. It cannot be lost from the human population. As long as it was not there, it was not there. But it ensures its survival once it enters the population. So once the plasmid enters, sorry, excuse me. Once the plasmid enters, can you all hear me?
Yes, sir.
Hello?
Yes.
Yeah, so I'm just sort of checking. So once the plasmid is inside, it cannot be lost. Because if it is lost, the cell will die. So the plasmid ensures that it becomes essentially like a parasite. It cannot be lost. So such plasmids can then be used to carry whatever genes of interest that you want, and you don't have to make any selective media. Your media is no longer, you don't need any media which select for the plasmid. Notice that earlier the media had to contain antibiotic or not have leucine. Either it had to have something absent or something present to ensure plasmid survival. But here the media is not an essential help for the plasmid to be maintained. Because remember earlier, you could always get rid of the plasmid by simply removing ampicillin, and slowly over a period of time, slowly but surely, plasmid free cells will emerge and they will overtake and they will survive and the cell will become plasmid free. Of course, it will take a lot of time. Similarly, leucine, the moment leucine is present, plasmids will be lost. And so to maintain, you have to either add ampicillin or subtract leucine. But now you don't have to do all this. Using a similar strategy, people have done something very, very clever, because they wanted to add leucine and they wanted to add complex media. Because as I said, it is associated with cost. Many people, what they did was that let us go back to this original problem. Exactly following this logic, they did the same thing. They took the cell and they introduced this plasmid which contains the leucine gene, leucine 2 gene, and they cut out the leucine 2 gene from the chromosome. So in the chromosome there was no leucine 2, so this was auxotrophic complementation. But they also cut out the leucine 2 transporters. Leucine transporters. So now once you cut out leucine transporters, you cut out leucine transport, then this cell cannot survive unless the plasmid is there, because it cannot take up leucine anymore. Of course, it's not easy to cut out leucine transport because complex nitrogen sources are often taken up as dipeptides and monopeptides and so on and so forth. Let us not get into that complicated argument. But theoretically, let us say that if I cut out leucine transport, this cell will now always have to have this plasmid. Because without the plasmid, the cell is dead. Now, can you tell me why such strategies are not very easy to implement? Can you think? I want you people to think.
We have to cut out the gene. That is not easy.
No. Suppose we cut out the gene. Suppose we cut out the gene. Just think about it. What have we done? We have made a mutation here, which is LEU2 minus. So there is the cell cannot synthesize leucine, right? Okay?
Yes.
The cell is an auxotroph. It cannot lose auxotroph. ठीक है ना?
Yes,
and it does not have leucine transport.
Yes.
So when will you transform the cell? You want to transform the cell, right? You want to take this plasmid here. Think about it. You understand the problem here? I'll let you think about it. Why do you want a plasmid inside the cell? You want a plasmid inside the cell
Produce leucine.
because you want your gene of interest to be inside, right? So you will construct this plasmid with the leucine 2 gene, etc., etc. You will construct this plasmid with the gene of your interest and leucine 2 and so on and so forth, and you will introduce it inside the cell by a process called transformation. To transform the cell, this cell has to be alive.
Yes.
Right? But how will it be alive? How will you grow this cell to transform it? Because this cell has no leucine transport and it has a leucine 2 if leucine 2 transport as well as LEU2 has disappeared, then in all media the cell will die. Cell will die.
Sir.
So then how do you sort of, this is a very good theory which is completely impractical. You understand? It's a very It's a very nice thing on paper, but how do you implement it? So these are sometimes very good ideas on paper, but then you discover that there is a fundamental flaw. The fundamental flaw is that how will you get the cell available so that you can insert, because you cannot just insert the plasmid, you have to first insert the gene which is of interest. After all, this gene is making the protein which you are really finally interested in. So to make the gene, you have to insert it in a test tube and then put it back by a process of transformation. And if the cell is dead, then you cannot put it back because it survives only when the plasmid is present. So really these are very difficult things to implement, because what you do is that you normally transform a cell which has leucine transport as positive.
So, but why would they remove the transporter in the first place? Because
I will tell you
even
why.
they would.
And after that, I will explain this to you. And after that, after you insert the plasmid, then you create mutations very, very cleverly, which is not very easy, and get rid of leucine transporter gene while the plasmid is already present. Now this cell becomes your industrial strain. Now this cell industrial strain. This is your industrial strain. This is your production strain. Now this industrial strain has the advantage that whatever be the media, this plasmid now cannot be lost. Because if it is lost, the cell will die. Okay, so therefore, when you keep your culture in storage, if plasmid free cells emerge by some kind of accident, they will die. So you are absolutely 200% sure that the plasmid is always inside, and therefore the gene is always inside. So now this will survive under all media conditions, and now you can grow it in large amounts of complex media, because the complex media contains leucine, but you are not bothered. Because now your plasmid is always present, and the cell which loses the plasmid will be dead, even though leucine is theoretically available from outside. Because the leucine part has to be synthesized by the cell. The complex nitrogen will provide all the other stuff, including also leucine, which the cell will not take up. Doesn't really matter. So really, such industrial strains are very, very difficult to make, and they have all kinds of issues which I will not get into, but they are very, very stable, and they ensure that your system is very perfect and your protein production is very high. Of course, nature finds a way against everything, and so I did not really talk about something which is which I will just mention in passing, that we are only talking of segregational instability. I will end it by just saying segregational instability, and end this section and go on to other sections, because we cannot keep on wasting time on plasmid instability. Now, which is the plasmid is lost. But there is also something called structural instability. Structural instability is more insidious. Structural instability is when the plasmid is not lost, but somewhere here in the gene of interest, as far as you are concerned, there is some mutation or a mutation in the promoter. So, point mutations, rearrangements, deletions, okay, point mutations, deletions, rearrangements, etc., which prevent gene synthesis from taking place. I mean, you are not interested in point mutations here if it happens. Really, as a technologist, your only interest is that it prevents gene synthesis. I mean, prevents gene expression, not gene synthesis. If it prevents gene expression and your product is not formed, you are in trouble, right? And product is not formed. And if the product is not formed, even when the plasmid is present, because the plasmid has undergone some kind of point mutation or deletion, and that mutated plasmid is now present. Why will it be present? And not the non-mutated plasmid? After all, this is 1 in a million again. This is also probability P. This probability P cannot be measured by binomial distribution. This is to do with mutation rates. But this very interesting mu minus, because it is a mu minus star, this cell is not one which has lost the plasmid, but lost the ability to express the gene on the plasmid. This structural mutant, rather than a segregational mutant where you have segregated and plasmid, it is not plasmid free. It is mu minus in a very strange way. It is mu minus not in terms of losing the plasmid, but only losing the expression of the gene of interest. This will again have higher growth rate, because this gene is the one which is producing a large amount of protein for you. And that protein production is actually slowing down the growth rate. Now the plasmid is present, so it contains all the markers that you want, and yet it is a mu minus cell. And there is nothing you can do about structural instability and say, sorry, please throw away the culture. There is nothing you can do about structural instability, because where the mutation has happened, because all the selection mechanisms, all the design features that you have incorporated to ensure that the plasmid remain inside the cell, and somehow X plus cells are superior to X minus cells. Now these X minus cells are no longer X minus truly. They are X minus in a clever way because they contain the plasmid. So this superiority is lost, and yet they produce no product. So they actually become superior in turn, because they do not have the load or the metabolic load associated with protein expression. What is happening? Sorry. I think I simply rub it out. So I think I'm pressing some
So I had a
buttons.
question.
Yeah, please go ahead.
So industrially, which of these like instabilities are more prevalent, like segregational or
Yeah,
structural?
I mean, actually, we have taken care of segregation instability by the mechanisms that I talked about. So while industrially 10 years, 20 years ago, segregation instability was the main issue. Nowadays, only structural stability is talked about, but it doesn't happen very often. And one of the ways to solve structural instability is not to solve it, but structural instability, to address structural instability is to actually create, because all structural instability has to happen by recombination events. And so recombination events, so you try to create recombination deficient strains. Therefore, you will see most industrial strains are recombination deficient strains, precisely to prevent mutations, rearrangements, gene deletions, etc. taking place even in the plasmid. You cannot, unfortunately, make a completely recombination deficient strain. These are the things that they will not teach you in molecular biology. In molecular biology, when they teach you, because they believe that you are Sida Sada BTech students, you don't need to understand complexity, they will tell you all molecular biology, all recombinant DNA technology is 0-1. It is never 0-1 in biology. It is always 50 shades of gray. Now, therefore, you only talk of higher probabilities and lower probabilities, and that is what makes the life of a fermentation person or a bioprocess engineer so much more difficult, but also so much more interesting and challenging. So you can never make a complete recombination deficient strains will die for reasons that you have to understand. So you can knock out various recombination causing genes, and most strains industrially are recombination deficient to a large degree, and that reduces the probability of making structural mutants, does not make it 0. So yeah, let me sort of end it on this note and say we will not talk of recombinant protein production anymore. We will not talk of instability anymore. This is to give you a flavor of the problem, the solutions available, and the fact that the solutions don't always work. This is the whole story. I mean, I always feel that you people are now engineers, and whenever I talk to you or teach you, I do not want to get you into research. But I also want to tell you that as people, we tend to lose against the bacteria. We keep on trying to cheat the bacteria, forcing it to do certain things. The bacteria says, no, I'm not going to do it. And almost invariably we lose. But we make partial victories, and that is what is enough for us to continue our dukandari against the bacteria. We can keep running our production systems well enough, but not in an absolute sense ever. Okay, so let me sort of stop it here. The class, at tomorrow's class, we move on from instability to the other issues, which is transcription, translation, and other aspects, which finally allow you to make the protein. So let me sort of stop here and say these are the two issues, structural and segregation instability. There's nothing much you can do about the structural instability. About segregation instability, they are the following active and passive methods that we talked about. Let us stop here, and if you have questions, you can ask.
Sir, I have a question, not a question, but like,
Yeah.
I mean, like, can't we add the leucine containing plasmid first, and then we will cut the leucine gene from the chromosome?
That is what we do. But then how will you ensure? Sorry, hold on. How can you introduce a leucine containing plasmid? भाई आप लोग थोड़ा सा प्रैक्टिकली भी सोचा करें, है ना? ये ड्राइंग्स कल मैंने क्लास में इसीलिए कहा था कि प्रैक्टिकल क्लास आप लोगों को समझना चाहिए. You see, there are 1 billion cells. There are 1 billion cells, even in 10 or 20 or 100 ml of it. And when you take these cells, 1 billion cells, and you add plasmid, and you add, billions of plasmids into it, most of the plasmids get degraded. You know how many cells of these 1 billion cells get transformed? At the most, or 1 lakh cells get the plasmid. Plasmid goes inside them when you do transformation. These are numbers which are very important, which means that 1 in 10,000 cells gets transformed. Now, why do you see this one cell and not the remaining 9,999? Because there is a selection marker on the plate. So the antibiotic kills 9,999 and allows the one cell which has got the plasmid to survive. And this cell becomes larger and larger, and you can see on the plate, when you plate it, you see colonies on the plate. That is why I wanted to tell you about the practical aspects of this course. Now you see colonies on the plate, which means, and all this here, all the stuff here is actually full of the dead cells. You see, all the here is dead cells, and the ones which have formed colonies are the ones which have. So always when you do transformation, you need to have a very strong selection mechanism which kills everything else. Unlike mammalian cells and CRISPR-Cas, where sometimes transformation efficiencies are as high as 90%, but that I will not talk about. In mammalian cells, sometimes you can get even 50% of the cells transformed, or rather actually transfected. Okay, transfection efficiencies, unlike transformation efficiencies in mammalian systems, are very high, but then the number of cells are very low, and there are mechanisms why, there are reasons why transfection is so high. That I will not get into. Yeah, go ahead. That is why various technologies like CRISPR-Cas, etc. Again, you people have not done recombinant DNA as a course, right?
No, sir.
Yeah, that's a bit sad. I should not be teaching this stuff unless recombinant DNA technology has been taught. So I can understand that there will be some difficulty because these are all, I'm assuming recombinant DNA technology, and I cannot assume that. So I have to keep on telling you about recombinant DNA technology as well in this course, which is not my job. I am not a biologist, I am a chemical engineer. So let us, get back to the basic argument at hand, which is that your transformation selection has to be very, very good, 1 in 10,000. It should kill the 9,999. Now, what you are suggesting would not kill them. And so, how do you screen? You cannot pick 10,000 cells one by one and say, "Arey, isme plasmid gaya hai."
Yes, sir. Sir, can you please briefly describe what is transfection and what's the difference between transformation?
अरे भाई आप बाद में आप लोग करेंगे ये सब चीज चलिए ठीक है ओके if you say so. Transformation, you grow the cells, and after growing cells in a flask or something, you grow the cells, and then these cells are made, well, let me not get into very complicated stuff. Essentially they are made by various chemical treatments. Calcium chloride is one of them. Washing them with cold calcium chloride is one of them. They are washed in cold calcium chloride. They are made competent. What do you mean by competent? Competent, भाई आप लोग competent है कि नहीं है? Or competence is always with respect to something. They are made competent to take up DNA. Under normal situations, cells can take up DNA, but if you damage the surface of the cell wall, because remember this is negatively charged and DNA is also negatively charged, so you somehow sort of damage the cell wall so that it can take up DNA. And the plasmid is sitting outside, this DNA is there. Normally, extra DNA cannot enter the cell. So you make them competent for uptake. Now, nowadays we use electrical signals rather than calcium chloride, so we call them electrocompetent. We simply use an electric capacitance, we build up the capacitance and we give a huge volt jerk across this, and the DNA just sort of pushes inside. Sometimes we add dielectric constants like PEG to improve uptake, polyethylene glycols. There are all kinds of tricks with other kinds of cells. You don't have to bother about the basic principle. This is just a technique. It has been optimized by molecular biologists. Essentially, the idea is the plasmid sitting outside should get inside. It should overcome this barrier of the cell wall. And then Obviously, if it was just a simple piece of DNA, it will get chewed up by the endonucleases. But this DNA is a circular DNA, and we ensure that there are no sites, etc. I mean, those are more complex questions that it is able to now replicate inside very, very comfortably. So this is called transformation in bacterial cells, and for reasons that I will not get into, it's called transfection. With the methods, the strategies are different in mammalian cells. Because mammalian cells now have become very important production platforms for complex proteins, especially monoclonal antibodies, and so many things, and all kinds of cancer treatment, monoclonal antibody production, etc., etc. These cannot be produced by E. coli. They are produced almost invariably by mammalian cells because they need to have the fine structure. Let me say, let me not get into complicated stuff again. They should have the glycosylation pattern. You heard of glycosylation? So a specific glycosylation pattern which matches humans, which matches the human product, matches the original human based protein. Otherwise, there are all kinds of immune reactions. So to get an exact glycosylation pattern, you need to use mammalian cells. You have to transfer them. Okay. Stop here.
Yes, we can.
Thank you. We'll talk in the next class. We'll stop here.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Okay.